Okay, in this video, I would like to discuss subtopic 8.3. It's about heat conduction. So in this subtopic, you need to know three things. One is about definition. Another one is about heat transfer. So given the formula here. And then you need to know how to describe the graph of T against L. First of all, I would like to go through the definition. Here, the definition for heat conduction. What is heat conduction actually? It's a process where heat is transferred through a solid from region of high temperature to a region of lower temperature. By direct contact of matter. So the key thing here is that the heat flows from higher temperature to lower temperature. Okay, so by that definition, you actually have this formula. So Q here is actually the heat. So I think you learned before this that heat is equals to energy. It's basically heat, energy, and Q over T is basically rate of heat transfer. And this one is equals to negative K A delta T over L. If you look back to the initial definition here, the heat will flow from higher temperature to lower temperature. So in this example, we have 100 Celsius and 50 Celsius. So obviously the heat will transfer from 100 to 50. Q over T. So that means our final temperature is 50. Our initial temperature is T1. Initial temperature is 100. So this would be my T1 and this would be my T2. So if you want to determine the delta T, it should be T2 minus T1. So you can see that this one is smaller than that one. So you get a negative over here. So this one cancel out. And you get positive rate of transfer. L is defined as, I think right over here, as defined as distance between hot and cold. So that one would be this one. End to end distance. And then A is the surface area over here, cross sectional area. And then delta T is basically T2 minus T1. And then you have K. K here is the thermal conductivity. So K is basically determined by the type of object. So example for different material like steel, or maybe you have a nickel or a glass. So those have the different values of K. So higher thermal conductivity means that it is easier to transfer heat. That means bigger K means a good conductor, lower K means not so good conductor. So the unit for K is W minus 1, M minus 1, K minus 1. And then this one is an example for heat conduction through joint rods. So here, let's say if you have two different material X and material Y. So let's say you put some source of heat over here. So let's say this one is 100, maybe 80 degrees Celsius. And this one is basically maybe 50 degrees Celsius. So obviously the heat will transfer from higher to lower, like this. And this one is Q over T, rate of heat transfer. So if I want to determine the T at the junction there, so then I have T1. Maybe I can label this one as T2 and T3. So in question, they will say that at one point, they will reach a steady state. Steady state means that you have an equal rate of heat flow. So basically over here Q over T and over here Q over T for Y is equal. So I can write it down as Q over T for X is equals to Q over T for Y. And you know that this one is equals to negative K A dt, sorry, delta T over L. Similarly, you have negative K A delta T over L. So if you have the same dimension, like A and L is the same, then you can cancel out. If not, you can't. So K there depends, like this one is Kx and this one is Ky. Obviously different material, you have a different K. And then the key thing here is about this delta T. Okay, delta T for X is basically from here to here. So it will be T2 minus T1. On the other hand, for Y, it would be T3 minus T2. Okay, so basically, just now, I will explain you about the definition. And then about this formula. So I won't show you any calculation yet. Okay. And then now we will discuss about graph, which is T against L graph. Okay, so for this one, you need to know you have two different materials. One is when, this is when the rod is insulated. And then you have another case when the rod is non-insulated. Okay, so if it is insulated rod, you can see that the heat flow parallel like this. So all the heat transfer from one end to another end. Okay, so no heat escapes from the side of or to the surrounding. So if that's the case, then the temperature gradient would be this one. Okay, so if you go back to this equation here, temperature gradient is actually this one. So I write it down there. This is what we call temperature gradient. So basically, if you have a graph of T against L, the gradient here would be the temperature gradient. Okay, so bigger T over L, steeper the graph. So here, since the heat is properly insulated, the values of temperature gradient is constant. Okay? So you basically have a straight line over there. And for case for non-insulated, you can see that from this diagram that the heat actually flow out from the material. So because of that, as it goes further from the higher temperature there, or that source here, so you can see that the heat actually decreasing exponentially, right? Because there's heat loss, okay, escape from the site. So for this one, there's no calculation that you guys need to know, but you need to know how to maybe draw this one or draw this one. So you can see that as it goes out, as it goes further away, QT becomes smaller. So the gradient from steeper becomes less steep. Okay, same goes for the QT and delta T over L. This one is the temperature gradient. Okay, now let's say if you have two materials side by side touching each other, and you have, this is the first, this is T1 because this one is higher temperature compared to T2, right? So the heat will flow from there to there. Okay, what happens when steady state has been achieved is that the heat flow through both material is the same. So like I told you before, so QT for X is equals to QT for 1. This one is material 1 and 2, so QT for 1 is equals to QT for 2. So from there, I can substitute that K A d, this one should be delta T over L equals to negative K A delta T over L, right? So this is a constant value, right? Because this is equal, so I'm running out of space there. So that means everything is constant, like A and L is constant, or maybe A is constant, because this one is side by side, right? So K is actually, if this one is equals to constant value, I bring it over here, then you go 1 over something. So you can see K is actually inversely proportional to this thing. So K here defined as thermal conductivity. Okay, like higher K is a very good conductor, heat conductor. So let's say if you have a low K, then delta T over L is higher. So that means the temperature gradient will be bigger. Okay, example over here, let's say for this one. So let's say we compare material 1 and material 2, where K1 is less than K2. Because it is inversely proportional, that means delta T over X is bigger. So that means over here you have a steeper compared to that one. Okay, and then if you have K1 that is bigger than K2, that means this one is smaller. Temperature gradient for one is smaller, so less stiff, more stiff. Dia terbalik lah. And then for non-insulated, if you have two materials side by side, okay, just now it's insulated, so no heat loss. Now it's not insulated, so you have heat loss through the surrounding. Again, T1 is bigger than T2, so you will expect the heat will flow from there to there. So T1, maybe T2 and T3 over there. Okay, and then if K is different, you will expect that the steep will be different as well. The gradient will be different. Same goes over here lah. So K is inversely proportional. I mean, you can't really say like that because this one, there's a heat loss, right? But you can expect that this one, if K is smaller, delta T is bigger. So that means over here, you expect K is smaller compared to that one.
She says that she loves